Yep. So yeah. Hi everyone. Ian Fox. I work in NRDD, which is sort of Network Rail's internal design group, I want to call it. So I'm senior design engineer. I work predominantly in the northeast, but we do work collaboratively with all of our design officers, so we can do design work all over the country. What I thought I'd start with, I wasn't sure what level everybody was at in terms of drainage. It seems to be, some people seem to think it's very easy. Some people think it's a dark art. Others just seem to have no clue whatsoever about it. So I thought I'd give you a bit of a brief overview of the drainage that Network Rail do. And then Matt's going to have a look a little bit more at some case studies of where we put it into practice and some of the things that we've done, certainly on some of the Transpennine route upgrade scheme that Matt and I both are part of at the moment. So if everyone can see the slides, I thought we'd have a quick look at very, very basics of what drainage is, why we need it, the standard that Network Rail have, which is CIV 005. Obviously, because we're Network Rail, we have some standard designs as well. A tiny little bit on catchment analysis, which is a massive topic all of its own. We'll have a look at some of the future ways that drainage is going. And then there might be some time for questions. I'm hoping this lasts probably 15, 20 minutes, and then we can get into the more exciting stuff that Matt's got. So the basics we'll have a look at. Well, people think it's just pipes and catch pits, isn't it? Is there anything else to drainage? We'll have a quick look. Why do we need drainage? A lot of places, historically, certainly with British Rail, drainage used to be the first thing that was pulled off a project when it was going over budget. It was, we'll just remove the drainage and we'll build everything else. So why do we need that? As I said, the standard, have a look at what that says. We'll have a look at some designs. We'll have a look at a little bit of catchment analysis. And then we'll have a look potentially at some of the innovations that are coming along to help us with drainage design and water management. A lot of this is based around the idea that if I say to you, I'm a drainage engineer, everybody assumes that I deal with pipes and catch pits all day, every day. If I tell you I'm a water management engineer, that evokes a little bit more of what I do. We don't just look at pipes and catch pits anymore. We have to look at the wider world. We have to look at third-party land. We have to look at runoff. We have to look at climate change. There's all sorts that go into managing water around a railway. It's not just pipes and catch pits. Saying that, the actual drainage system is pretty much pipes and catch pits with a few additions. So this is a typical drainage layout of what would be under the track or off track. So there is off track stuff. So that could be, I don't know if you can see my cursor pointing, but we could have a crest ditch. You've probably all seen those. We could have a pipe running along the crest with some catch pits in, with some spur pipes coming off. If we've got a slope drainage, we have a slope that requires water removing. We've got some herringbone drainage that catches that water on the slope and brings it down to track level. We can have cascades. Now they could just be a straightforward pipe that brings water from that crest ditch down to track, or we could have it as an open cascade. And then the track drainage itself is pretty much pipes and catch pits. So there we've got two CES systems and a 6-foot system. I've never ever seen that built with so much drainage in, but that's the type of things that we could have in one whole area for drainage. So what else have we got? We've got pipes, we've got catch pits, we've got some cascades. What else have we got? Well, we've got some head walls every now and then. They're very good for transferring open ditch to a pipe or the other way around. These are getting more and more used now. So part of the risk management stuff and part of the water management thing, you need an outfall. What we're finding is where our drainage systems outfall into a public sewer, for example, the flow rates that were allowed into that public sewer are becoming less and less. And where we have an existing connection, we're actually being asked to reduce that connection by 30% or more. What that does is that allows the water authority, whoever that may be, That 30% reduction in flow allows them to account for climate change in the future. That's where the 30% comes from. It's a sort of standard number that they've adopted. But that means that we're now having to attenuate flow within the railway. We have to store that water somewhere. We can't just dissipate it. We have to find a way of storing that. Now, the way that we're doing that at the moment, there's a lot of cell crate storage going in. We don't really like open water courses next to a railway for obvious reasons. So we're trying to store that water underground in cell crates, which are these things on the screen now. Big open hole, drop lots of upturned milk crates in, and that'll store the water in there for you when you've got the outfall. The flow control will limit the flow. There's no moving parts in that. That will limit the flow to a certain velocity, which will allow us to outfall into the public sewer under regulation. But there is lots of other things. So as I said, this drainage engineer or water management engineer thing, it evokes different outcomes. So we need to consider catchments. We need to consider where we're on third-party land. We need to consider consent authorities, the ecology. We even need to consider other disciplines sometimes, like track signalling. We need to consider the topography of the land. Which way does the water actually want to flow? Sadly, I've never found a way yet of making water flow uphill without pump. I mean, I'm a rich man when I do find that, but at the moment, we have to stick to the topography of the ground. We have to make the water flow with the gradient. And above all else, the most important thing in any drainage system is having somewhere to put the water, having an outfall. If we don't have that outfall, that drainage system is not going to work because the water is just going to back up and back up and back up. Why do we need it? Well, I think the consequences are pretty obvious to everybody, really. A very extreme example is Stonehaven. Obviously, lots of reports about that in the press and from government reports at the moment come out. The final reports just come out. Didn't show Network Rail in a great light. We have delay minutes, we have passenger disruption, we have damage to assets, and essentially we have an additional cost to the taxpayer, which is, we're spending public money at Network Rail. We have to be cognizant of that, and we have to be mindful. Quick quiz then. London North East and East Midlands area. I don't expect anyone to answer. I'll just give you the answer. 4 questions. So how many delay minutes do you think have been attributed to flooding just in LNE since 2009? How much did they cost us in delay minute terms? What percentage of delays were caused by a blocked outfall? And a funny one in litres, how much rain falls on the route every year? So delay minutes, you can all take your guesses. We've had, since 2009, just in LNE, 200,000 delay minutes, roughly, based on flooding, which is a hell of a lot. They cost us 2 million quid in fines. Now, that doesn't include any cost of remediation. It doesn't include anything at all. That is just the delay minute fine, 2 million quid. What percentage of delays were caused by the outfall? So previous slide, I said outfall is the most important thing. 80% of those delay minutes were caused because the outfall had stopped working or wasn't there. That's a massive number, a huge number. And in litres, we get around about 106 billion litres of water fall on the route every single year. Now, please don't quote me on that, and please don't try and do the back calculation to work out if I'm right or wrong. Just take it. I've just made it up, but it's fine. So, why do we need it? Particularly to track. Sites with poor drainage tend to have roughly twice more track faults than areas with good drainage. They tend to have roughly 6 times more wet beds per mile. And we've got more twist faults with poor drainage. We lose that formation level, we lose that ballast retention, and we start to get twist faults. That means the maintenance goes up on these sites. So we require 3 times more tamping, twice as much manual lifting, and 4 times more money spending on maintenance. 4 times more money spending on maintenance. So if you think how much a maintenance on a piece of track costs, and then compare that annually with how much improving the drainage system would cost in that particular area, you can see where this is going. It's much more economically viable to improve the drainage and get rid of that maintenance cost annually. But also, I'll show you some of these before I come on to that, actually. Blocked outfall, not great. Ballast, we've all seen this. Ballast in the catch pits, the water's not going anywhere. That's not a road, that is actually a train track that that guy stood on. I actually stole that from one of Matt's slides previously. And again, we've all seen this when we're looking in a drainage system. You can just see sludge, silt, where the system's performing ineffectively. It could be a collapsed pipe, it could be just a bad design, it could be all sorts of things. We have a management process which goes through a whole host of things of what it is that we're supposed to do. So it describes the assets, it tells us the management plans, it shows us how to do assessments, surveys, evaluations, design, maintenance of those systems. And that's there really to stop this. So one of my bugbears with Network Rail is that if we have, for example, a landslide, or if we have an issue with a track or an OLE stanchion or something, the press headlines tend to be Network Rail engineers working round the clock to restore line to fix problem. With flooding and with water, every headline has a negative connotation. So every headline tends to show you, for example, that bottom right, queues of really annoyed passengers stood in a line wondering where their trains are. The headlines tend to be damaging and provide reputational damage to Network Rail and to the railway industry as a whole. And it's all because of drainage and water management around the railway. As I said, Stonehaven's a prime example of this, where the Network Rail drainage system worked perfectly. The off-track system that on third-party land did not. Now, if you've read that report, there's a few contributing factors. The design that was on the paper was not the one that was built by the contractor. The contractor built something a little bit different to the design because they didn't want to build the design for whatever reason, which led to a failure. But it's still a failure of a drainage system, which has caused fatalities, which is not something that we ever want. But it's those type of incidents that cause the negative connotations around this. We do have standard designs. We have standard designs the same as anybody else has them, just to maintain consistency, gives us a benchmark, ensures safety, and provides, where appropriate, some quick design checks. We can tell very quickly if someone submits a design for us to have a look at, or we do our own design. We've always got some quick reference points. And as long as we stick within these parameters, we know they're tried, tested, and we know for a fact that they're going to work on the railway. The railway is a very different place to manage water than the highway or third-party land, farmland, within town, cities, etc. The railway is a very unique environment to manage water in, and it has its challenges. It really, really does. So these standard designs try to give us some sort of continuity when we're looking at this stuff. They do cover a whole range of scenarios. They provide a great way of accepting designs. We can use to check the deviations, but it will allow for rapid assurance, which is one of the things, certainly on Trans-Pennine route, that we need. We have a fast turnaround process. The scheme's going to last till 2030 something, but the design and the construction time are very different. The construction time's taken up most of that, and the design's very quick to turn around. And again, we need to think about that we're spending taxpayers' money here. So anything that's going to maximise efficiency and lower costs has got to be a good thing. So for drainage, we've got roughly 13 standard designs. We've got a few more coming in shortly. I was going to actually flash some up, but I think we'll probably skip through that, and I'll share this presentation if anybody wants it, and you can click on the links and get those. Catchment analysis. This is something that is a big area. You can do whole degrees on catchment analysis and hydraulics. I'll try and condense it into one slide. It's like saying I'll do the whole history of the human race in 10 minutes. Right. With catchment analysis, we have to look at huge amounts of data. So essentially, when we're looking at a catchment, what a catchment is defined as if a drop of water falls on a piece of land, will that drop of water eventually make its way to your point? So your railway or your bridge or your road or your garden. That's your catchment area. Anything that it can flow to that particular point. So when we're doing our calculations to work out the size drainage that we require, we need to know how big that catchment is. We need to look at the contours, the topography. Is it a really steep catchment? Is that water going to get there very quickly? Or is it quite flat and it's going to get there quite slowly? The further up to the top of the catchment that you get, so again, if you can see my pointer, when you get up into the hills, that's what we call a flashy catchment, a really fast reacting catchment. It rains, the river swells pretty much instantly. By the time you get down towards the sea, which is where most of these things end up, they tend to be quite flat, quite shallow, they tend to be quite slow moving. And the reaction time from the rain to the river swelling and causing problems is actually could be several days. So we need to think about that. We need to think about if we've got any contributing water bodies. Is it just this particular catchment, or are there other areas of water that can come into this one? We need to look at, are there any ponds, rivers, anything like that? It doesn't take into account existing drainage features. So if we've got a major road, major railway across a particular catchment, most of that water should get caught. So for example, we've got the M1 running across a piece of Transpennine route, for example. Our catchment may still extend beyond that, but we have to think about a lot of that water will actually get caught in the M1 drainage network, and it then won't come as part of our system down in the railway. So there's parts of that we need to think about. There is an FEH website, so the Flood Estimation Handbook. It used to be a CD-ROM that you could buy to click on and get catchment size, catchment descriptors. You get things like the urban extents, so that is how much built-up catchment is within it. That'll tell you things like how much roof space, or how much driveway, or how much paved road there is. Obviously, any water that hits those surfaces, they're not going to go into the ground. They're going to run off, and they're going to run off very quickly back towards your asset. So there's lots of descriptors that go in there that gives you standard annual rainfall and all sorts of things. And once you've got all that information, just to complicate it slightly more, there's several different methods of working out the flow rate that's coming into your asset. So there's a one called IH124, developed in 1994, and still in Network Rail's drainage manual as the method to use for small catchments. Now, I'm not sure about you, but 1994 was quite a long time ago. Technology's moved on, and our understanding of this stuff has moved on. RefH and RefH2, so RefH2 was actually invented, for want of a better word, in 2013, which is a much more a robust method for working out flow rates, for working out catchments, for working out the volume and the amount of water coming into your catchment. So where we can go against standard in this area, because the technology is moving and improving faster than our standard is getting updated. So we can go against standard in this particular instance. There are training courses available. There's training courses on the FEH. There's training courses on some of the other software that we use, micro drainage, ICM, etc. As I said, there's whole degree courses, but if anybody wants to know any more, then feel free to get in touch, and I can put you in touch with the relevant areas. And then we'll look at some advancements. Computer processing power is obviously increasing. As I said, technology is increasing. We've got this thing now called CFD modeling, computational fluid dynamic modeling. That's the first multicolored picture at the top there. So what this does is take a 3D CAD model, and you can drop on a rainfall event, and you can actually see in real time how the water flows around. And it gives you energies, it gives you shear stresses, it gives you Shields values, it gives you uplift, buoyancy, turning, all sorts of hydrodynamic and hydrostatic forces. And you can see how your drainage system is going to react. You can see for scour, for example, which we'll touch on in another one of these. We use CFD modeling in scour quite a lot to work out the location, the depth, and the impact that the scour has on our structures. But we can use it in drainage. There's a very good piece of software called ICM, InfoWorks, that does a very good drainage system analysis, where it'll give you surcharging, flooding, it'll give you the surface water flow directions. There's lots of improvements that come with these computer processing. As with everything else, you need the information to go in there, and you need someone who understands that piece of software to use it. But the development's there. We have a much better understanding of weather. We've got weather radars, satellite data. We've got all sorts of weird and wonderful things up in the sky that tell us what the weather's doing, and we can track it. Our 5-day weather forecasts now are very, very accurate. 7 days plus, not so much yet. There's some R&D projects going on at the moment that uses what's called ensemble weather forecasting. So if you look out the window now, you know what the weather is like right now, right this second. In 10 minutes time, we could probably model and tell you what the weather's going to be doing quite accurately. But there's that many variations in temperature, pressure, wind speed, everything. There's lots and lots and lots of factors that affect the weather. And we use, 50, 60, 70 different models of different variations of that model. What happens if the pressure changes? What happens if the temperature changes? To work out the probability of rainfall within certain areas. So we're using that at the moment. As I said, there's a R&D project going on at the moment for that. We have more data. We started monitoring very closely flow data in rivers, rainfall data, probably early in the 1900s. And we've got lots and lots of that data that we can use within our models and our predictions. We've got the 3D CFD modeling. We've got some advanced machinery. So this was a picture that Matt sent to me this morning to slide in here. This is a trenching machine that's been adapted to an RRV. Now this has just got, you probably can't see that picture. It's got basically a very large cutting disc that just slits a trench, quite often used in farming, but never really adapted to railway. So I think Matt might hopefully be able to tell us a little bit more on that when we speak to Matt in a sec. There's our R&D project, the real-time surface water flooding software. So JBA Consulting have invented this piece of software. As I said, using ensemble weather forecasting, it looks at our asset map, and it will tell us the risk of surface water flooding to those assets. We already have fluvial flooding, which is river flooding maps, but this is surface water. This is something quite different. There is also another piece of software called GroundSat, which looks at how saturated the ground is before the rainfall. So the satellite imagery can actually, give you an indication of how saturated your ground already is. As we've mentioned earlier, micro drainage and ICM updates, and then we've got some real-time monitoring R&D projects. So if you come back for the Scour one in a few weeks, a month's time, I'll give you a bit of an idea of what we're doing for real-time monitoring on Scour. And obviously the impacts of Stonehaven on us as Network Rail drainage people are huge. There were 12 recommendations within that report that were aimed directly at Network Rail. And as I was reading it, 5 of those were aimed directly at me, because the 5 recommendations took into account exactly what I do as a job. So it took into account extreme weather management, drainage design, scour, just all sorts of, as I was reading it, I thought, well, that's me. So we're still trying to understand the impact of that report, and things are going to have to change within Network Rail and the railway industry, because we need to manage water better. Historically, they've put in the biggest pipe that they can, and then they've walked away and left it. Maintenance hasn't been there. The thought processes haven't been there. The design hasn't been there. It's been a lot of the time as though we've got water on site. I just put a pipe in, we'll, move it away. We are getting better, but there's still a lot of room for improvement within this. And yes, the old climate change. It is happening. I don't care what anybody says. You can look at all of the data that we have, and you can see that flows and the amount of water that we're dealing with is increasing constantly. Quick summary then. It costs us millions and millions of pounds a year, and we need to get better because we are spending public money. It is just more than pipes and catch pits. There's a whole lot more to drainage than just pipes and catch pits. We have quite a lot of tools to help us along. It is still a very specialist area, but as I said, it quite often gets forgotten, and it's quite often the first thing that gets removed from a scheme when it starts to go over budget. And as Brunel said, drainage, drainage, and then some more drainage. That's pretty much the key to a success. We'll pause there for a couple of seconds. Does anyone have any questions on any of that before we go to Matthew?
There's no questions as such in the chat. If anyone would like to raise something, I think Luke's put a comment in about Arup and a link to what the about spongy cities. But has anyone got a burning desire to put a question to Ian at this stage? Or
I think they all might be asleep, David. I think
yeah, no, they're not. They're fully engaged. Lee Riley's asking about, have you any information about the trenching machine? I think that might come up in the next one.
It was hot off the press this morning, so we'll keep you posted with that one. It was literally an email at 8:30 this morning that said, "Look what's been adapted. Maybe we need to look at this and go and have a look at it."
There we are, cutting edge. So what software do you use for the CFD analysis?
So the CFD is generally used with, we have a contractor that does it, and it is Flow 3D from Flow Science, an American company, and it's very, very interesting when you start and look at the CFD stuff. There is some free versions. There's a version called OpenForm, which is one of the universities, I think the University of Portsmouth, that's developing that. So there is some free versions of it. But yeah, Flow 3D is the one that you saw on the screen.
I've got a question there from Richard Wells as well, Secretary. Are we making any improvements in recording drainage locations?
We are, in terms of, a lot of things now can be geolocated, and the use of GPS is a lot more accurate now. The problem we've got on the railway is GPS requires satellite coverage, and a lot of the time we've got foliage above us, which sort of reduces the accuracy. But we are just not as fast as I would like it, to be fair.
Okay, all right. I think that's maybe, I don't know, are we okay to move on to Matt now, Ian?
Yeah, if I stop sharing my screen and we can pass on to Matthew.
We'll come back to that other question later. Thank you.
Good afternoon, everyone. Ian, you didn't tell me you were going to be that good. Thank you.
It's just a shiny presentation, Matt, that was all.
Get away with you. Right.
Matthew, is it worth going into full presentation mode just so we can see it better on screen? Yeah, that's the one.
Is that all right?
That's it, thank you.
Brilliant. Okay, so I can't see anyone's comments, but I'll pick everything up at the end, or if it's particularly urgent, please just interrupt. So, thank you, Ian. That's a fantastic overview. It set the scene beautifully for some pictures of drained iron mud, which is the space I occupy most of the time. So I put together a couple of case studies of recent work that hopefully will have some impact with everyone on the call. Certainly it's relevant to the TransPennine project, and I think, yeah, I'm a bit sad like this, but I think they're quite interesting in that they encapsulate and cover lots of different aspects of engineering, also topography, geology, history, and socioeconomics in some cases, and also sort of picks up a lot of stuff about how much we've neglected our drainage over recent decades. So the first case is not moving on, is it?
Are you still with us, Matt? He's just
still
dropped off
with you.
then.
Can you?
No, we've lost your screen, Matt.
Lost my screen. Brilliant. Won't be a minute.
There you go. You're back.
Just waiting for it to change. It's very slow for some reason.
We can see that now, Matt.
Sorry, Dave. What's it say?
We can see your drainage case study slide.
can't get it to move on, that's the trouble.
All right.
I'll just have to exit full screen.
Okay.
I'll keep talking. It's completely frozen now.
Yeah, that's good now.
That's moved. Okay. Right, so the first case study, sorry about that. First case study is Gilded Road on the outskirts of Leeds. So this is on the Huddersfield to Leeds line, which is part of the core Transpennine route west of Leeds. And this is a particularly bad spot. So what's the problem? It's an area of historically poorly drained track. Used to be a big intersection of numerous lines, but since it's been slimmed down over the past 40 years to just 2 lines away, up Leeds, down Leeds. Cutting with numerous overbridges, and it's the only site I know where the temporary speed restriction boards are kept stored on site, simply for ease of access. It suffers from persistently poor track quality, and the root cause, I think you'd agree if you looked at the right-hand picture, is poor drainage. Really, really high water levels, obsolete components, and time, really aged track components in a lot of cases, but fundamentally appalling drainage at or above sleeper bottom. It's not a flood risk site. The main problem here is poor ride quality, necessitating regular and very expensive temporary speed restrictions. So, as Ian mentioned in his presentation, outfalls are critical. So the first thing about this was to find the outfall, which proved harder than it sounds. So I did some jetting as a first step, trying to understand what's there and where the water ought to go to. And the jetting was inconclusive, but anyone who's ever undertaken any drainage jetting of any form knows how important sound is to helping understand problems and location of outfalls. So we could hear water being jetted and flowing underground. We couldn't see it. Obviously, it was at night, that didn't help, but still, the assets that were visible to us simply didn't help understand where the outfall could be. So I think you were involved in part of this here, with looking at maps on Teams during the height of the pandemic. But by overlaying old maps, it's possible to see some features emerge from the historic record. So in the right-hand picture, where I'm just circling my cursor, you can see there's a strange feature. It looks like a sort of geometrically shaped woodlouse with the 3 letters next to it, TKS. I took that to mean tanks. So I thought, okay, tanks. Now I know this site quite well because it used to be a terrible trespass and vandalism spot with dumping of tyres and burning of tyres. So I went to have a look, and that's what I found. Now there's water there, but where that water was coming from, I had no idea. So I decided to get some muscle involved. I'm very fortunate to be able to call on experienced contractors, not necessarily specialist drainage contractors, but groundwork contractors. So we've got a team at a site, and bless them, they de-vegged it, they removed the debris, and they dye tested from the last visible catch pit at track level, which I should have explained is on an embankment, which is 9 metres high. So we dye tested. 7 minutes later, the dye emerged in this morass, which is the site of the tanks. So I thought, okay, we're onto something here. We might have found a viable outfall. So I got some machinery in, and lo and behold, what emerged, it's like something out of Team, was a series of 6 interconnected brick-built chambers, obviously designed to perform a specialist function, which lost in the midst of time. So we carried on digging, and this team were fantastic lads, all young lads, and I think they really enjoyed it because it wasn't like a problem that they knew the end to. They didn't know the answer to this.
Yeah.
Treasure hunt, exactly. So, and I think it really got people's imagination, really stimulated people, and the quality of the work they did was brilliant. And they kept uncovering more and more, and the right-hand photograph shows what we got to, which was an inflow of filthy water, which would prove to be from the track drain. So, what did we find? Well, I think what we found was a drainage system installed by British Rail in the early to mid 60s, which was probably a pollution prevention intervention. And what we found was a cinder trap from an old loco depot, which is now long gone. It's now housing. So we found a cinder trap into which the track drainage had been connected. And then the pipe, falling out in a northeasterly direction, went to open watercourse. And that is all still in place. It's just that we didn't know it. I find this time and time again is that the various generations of railway people have done fantastic work at the time, and they haven't recorded what they've done very well, or they did, and we've lost the record. So I see it as my biggest challenge, and it's nice to see a question from the group on the chat about drainage locations. One of my biggest areas of concern, biggest areas of effort is plotting drainage and linking it up as a system. Because unless we understand drainage as a system, we can't really maintain it. And I know that Brunel said drainage. What he should have said is drainage information. So we just need to know where the stuff is and how it interlinks, and where ultimately it goes to. So, well, stuck on that slide. So that's what we did at site then. So we, once we'd got the pits, the tanks exposed, we did a further dye test from the last visible track drainage chamber. Dye emerged 3 minutes later. So we know we'd found something. We know we'd freed it up slightly. I ought to say that's the time taken for the dye to emerge. 3 minutes. It's only 30 yards away, so that's still very, very slow. We took all the debris away. We made it good. We fenced it off, so it's safe, because although this is Network Rail owned land, it's very close to public right of way, so we had to make sure it was secure, and that site is now fenced off from the general public. Next steps at this site will include, one thing I didn't mention was that, if anyone can remember the appearance of that water emerging from the inflow, it's utterly filthy. It's the worst quality water I've ever seen. So I went to the Environment Agency and said, I think we're inheriting dirty water here, and I really, really don't like passing it on. We're not equipped to treat water to get it into a fit state to discharge the watercourse. So can you please help Environment Agency on, tracking down the source of this pollution and working with us to mitigate the risk of passing on pollution to an open watercourse downstream. So blessedly, the Environment Agency came to site and we spoke to all the businesses upstream, and it was immediately apparent that none of the businesses occupying land upstream, all of whom connected into our track drain, ultimately via an ordinary watercourse, all those businesses had no pollution prevention measures on their areas of hard standing. They were discharging filthy water straight to surface water drains without treatment, without filtration. And we were inheriting this mess. The situation has improved now, but it's still filthy. That is that particular site. Now, I'd just like to briefly touch on another site, which is interesting operationally from a Transpennine route upgrade perspective. This is a site on the Calder Valley line between Mytholmroyd and Sowerby Bridge, for anyone who knows it. So it's a long way east of the border between North West and Central and Eastern. The site's called Wood Lane, and it was the most persistent flood risk site in the route, any route, I think. 13 incidents in over 5 years, cumulative delay of over 5,000 minutes, and it got to the point it was ridiculous that every time it rained, even pitter-patter rain, even a short, sharp shower, would flood here. And the big problem was not so much the flooding, it was the inaccessibility of the site. So a mobile operations manager or a PWI supervisor to get to site, it would take 2 hours to drive in heavy traffic, rush hour perhaps, and then an hour to walk, because there was no access point within a mile and a half. Really difficult access, as I say, but really disruptive if it flooded. One report from a driver could lead to 1,000 minutes. So something had to be done. Numerous attempts were made, initially by Ian's team, who did a lot of investigation work, but ultimately didn't really give us a design that could be implemented easily. So we started from scratch and went to site and had a good look around. found the outfall culvert, which is an original 1840s stone box culvert, ostensibly fit for purpose, but all the flow was beneath the invert slabs, which didn't help. However, it's not ours, so we have to deal with that one later. So on track, got a team to site with a vacuum excavator and exposed the damaged pipe. The root cause of the flooding was determined to be a complete disconnection beneath the 6 foot, which meant that water flowing in from the upside, considerable quantities just couldn't escape, and the pits would fill very, very quickly. Some really, really constrained capacity and absolutely no reliable outfall. So the decision was taken on the night just to renew everything cess to cess. In the interim, to try and mitigate those long journeys and the time taken I mentioned earlier, we installed a CCTV camera, which is one of the initiatives we're really trying to push to the fore, which is to have really sort of the best modern technology to give us information from site remotely, which saves unnecessary journeys, it leads to remote decision making, and it really builds resilience into the overall railway system. So we renewed all that, and that's before it was backfilled in tank. You can see there's another drain coming in there perpendicular to the under track drain, which was a service pipe for steam locomotive servicing troughs. So it was another site where we had to do a bit of archaeology as well. In this case, we had to cut through that because it's in the way. So, yeah, sorry, archaeologists. And this is all it was. It was a 9-inch land drain, effectively, that we had to accommodate, and we didn't accommodate very well. So it's just one of those solutions that seems so simple in retrospect, but at the time, it's deeply challenging. And as a last slide, just to give this was probably the last time it was cleaned out, which is a LMSR Victorian, well, probably not Victorian, actually, probably Edwardian uniform, but anyway, found by one of the team in the original Victorian culvert. Yeah, so next steps is install safe access route to maintain, install remote water level monitoring in the upside inflow to monitor water levels remotely, and then we can move conclusively from find and fix, which I hate, to predict and prevent, which is far more preferable. And that concludes my presentation.
Thank you, Matt. There's no, we've got a hand up, Olivia.
Yeah, it's kind of for both Matt and Ian, really. In the Northwest, we're finding a lot of the time that we just don't really have the space on the railway to attenuate any additional water. So we're having to look much more at the upper catchment and work kind of with third-party landowners on natural flood management. Is that something you've experienced and you've been working on as well in Eastern? I mean, we're only just starting to make inroads into it now. So if you are, then maybe we could share some advice or how it's going or something.
Yeah,
absolutely. So can I just jump in? I've got a live example, if that would help.
Yeah.
So site called Play Cross in Derbyshire, which we had really flashy catchment. Previous attempts would include 3 attenuation ponds upstream of the inflow to the railway system, none of which worked. The volumes of water were simply too high to control in any way. So what we did was we approached the local landowners and treated the catchment as like a long linear feature and installed leaky dams at sort of 100-metre centres all the way up the incoming watercourse with the permission of the landowner. And touch wood, that's been effective. So it is possible without buying land, obviously under licence with a third party, to manage inflows so that they don't present such a risk to railway operations.
Yeah.
We can speak offline if you like, Olivia.
Yeah, we're doing a similar thing with leaky dams. I was thinking as well, it's more kind of do with designs, how you incorporate that into a design, because it's really hard to calculate what the impact of the leaky dams will be on a system. So we can kind of do it, Matt, in our day-to-day stuff, give it a go and see if it makes a difference. But I guess, Ian, for projects like Transpennine Route Upgrade, it must be quite hard to put a tangible sort of figure on, well, if we did plant some trees or put leaky dams in here, this is what the actual impact would be on the railway. So
it's very difficult to quantify. Now there's two things with that. One, I'll talk to you offline about it, Livy, because I do have a contact in the Environment Agency who is head of natural flood management, and he has a team of volunteers up and down the country, and he has budget available, where if we're willing to work with them, they're willing to put natural flood catchment and natural flood management in upstream of our structures, and that could be quite good. So I'll talk to you offline about that one. In terms of how you calculate for the leaky dams, there are some documents that will give you some formulas and some ideas of flow rates and things. It relies heavily on assumptions is the only problem, because obviously it depends on how they're built, what they're built with, what the gaps are, how much of the watercourse they cover, how much into the floodplain they cover. There's an awful lot that you have to sort of look at, but yeah, we'll take it offline, and I've got some bits and pieces that might help you.
thanks.
Okay, I'll just, there's a couple of in the, I'll take the hand. It's just Shoaib. I was going to read out your question in the chat, but do you want to ask a question?
Yeah, thank you, David. I think it's really for Ian and Matthew, and I think this is just an overall question. Thank you for the presentation with the drainage. In regards to the unfortunate what happened at Stonehaven in Scotland, the incident because of the drainage, I mean, this is probably looking at the overall in the UK. From Network's point of view, Network Rail's point of view, I would like to ask is, because of that situation, in terms of looking at the overall drainage in the UK, especially under the railway, like for example, one of your presentations showed that they couldn't able to identify an outfall of a catch, the outfall of the water. Now, what is Network Rail doing? Are they doing the examination inspection of the whole UK railway network, where they're going to look and identify what areas do we need to consider so we don't allow for further, mishaps or further risks? If that's clear for Ian and Matthew.
Yeah, I think at the moment it's one of those ongoing things that Network Rail always look at water management, and they always look at where the water goes. Historically, it's only been when there's been an issue. So when we have wet beds, when we have a problem, that's when Matt and his team will go in and actually look around, as they have done with TRU, done some digging and actually proved and found the outfall. I think the challenge that we've got moving forward is where we've got water being managed effectively at the moment. In 10, 15, 20 years' time, that's not going to be the case, because climate change is going to give us more and more water onto the railway. So I think the challenge is how we look at systems that are working. And, it's quite difficult to go to the route engineers and say to them, okay, you've got a system that's working perfectly well here, but I want you to spend £1 million upgrading it so it's going to work in 20 years' time. Because that £1 million is going to be spent on another site that isn't working now. So it's an ongoing issue, but it's something that we're going to have to be reactive to. And if we get to the point in CP7 where we've got available funds that we can do a bit of proactive work, then fantastic. But I think Matt, do you want to come in on any of that?
Yeah, please. Just on the inspection, we have an annual inspection programme. So we inspect drainage fence to fence. Our inspectors are instructed to pick up, record condition of, location of, and attributes of all drainage, regardless of its function. The ultimate intention is to be able to map drainage systems with drainage condition and understand where outfalls are and keep them working. Now, I saw a comment come up there about outfalls. Is it not? So I'll just turn on my chat. I'll just try and explain that. So outfalls is just shifting the railway problem to someone else. So the purpose of, well, I think one of the fundamentals of water management is the notion of riparian ownership. So a lot of our drainage problems come from other people's water, either in too large quantities or from the wrong place. So if you think of a culvert that accommodates a watercourse, That was built when the railway was built, and the Act of Parliament decrees that we have to accommodate, the railway company has to accommodate that culvert. By accommodation, I mean ensure it's free flow without obstruction. Otherwise, flooding could be caused upstream. When we get people who allow water to freely discharge onto our property, we have to, first of all, ask them not to do it. And the second thing is to protect ourselves, put some form of measure in, be it a trench, a ditch, a pipe, to manage that water so we can control it. Now, where we have an outfall, they would have been established a long, long time ago. Where we need a new outfall, we have to abide by the conditions that we're set, either by the water authority, to be a private water company, or an internal drainage board, or the Environment Agency if it's a main river. So there's lots of things we do, and we don't pass on risk. I think that's fundamental to say. We don't pass on risk without working with people to mitigate that risk. I really don't like schemes that just say, well, once the water's gone beyond our boundary fence, it's no longer our risk. Because we have to be responsible asset managers and responsible water managers and work with all to make sure that water can be managed so it doesn't impact adversely on others.
Yeah, and just on that as well, just quickly, the Stonehaven report sort of criticises Network Rail for not understanding the drainage system that's off Network Rail land. Now, there's a little bit of a problem there, because if it's not our land, it's therefore not our drainage system. There's access problems. You know, if we find a problem, who then maintains that? So if we found, I won't use Stonehaven because that's slightly different, but Orty Hills, for example, in Scotland, another one where we had a big amount of soil that was washed down the slope. You know, if we had inspected that and found an issue, we ask the farmer not to do it. Then what happens if they refuse? Do we go on and actually do that work? You know, it's public money, but we spend it on private land. There's lots of issues, but as Matt said, we try and work with the landowners where we can. So yeah, it's difficult, and as part of that Stonehaven response, that, you know, some of the questions that were raised is quite tricky to answer, and we don't have an answer for them as yet.
I was just about to close. Just maybe one last question. Was it EB? Beeman? Sorry, I just missed the name there. Sorry, yeah. Any questions? Hand up.
I was going to say, just to add one more issue to that. I think the other thing is to help us improve on our outside drainage. We have to look at the inspection periods that we have, because that has got a big impact. Most of the time you find that some of the inspections don't come up with outcomes. So they go in there, it's overgrown with grass, and they haven't done that inspection and it's left. And to get back to there, it will take them a long time. So I think looking at the inspection period will help us a lot as well.
Hey, maybe Stephen, have you got a question?
Sorry, very quickly. More for Ian and maybe for Matt as well, I think. Yeah, network rate standard, it says, you know, for anything, if I'm not wrong, is it less than 200 hectares, you know, to use ADAS method? You, Ian, you know, as a designer and your colleagues, do you comply with that, or do you use FEH method, which gives you a far more conservative output?
We tend to do a bit of both, to be honest, Stephen. We kind of look at what's most appropriate for that particular site. So as I said, the IH124 method for small catchments is what we should be using for small catchments. In reality, that, you know, it might not be the most appropriate solution. So it's an area, as I said in the presentation, that we can go away from the standard. But like everything else, we have to justify that as to why we think it is most appropriate to use a different method.
Okay, I'll probably bring the meeting to a close. I don't know if people on the call who are still with us would like to just unmute for a second. I'll just a quick one. Oh, notice we've got the next section meetings on the 19th of May. We're looking to have a presentation on encapsulated rail solutions, and also just to remind you, I think Iain Fox is willing to come back and do a part 2 of this around Bridge Scour on the 21st of July, I think is the case.
Absolutely. I'll come and bore you all again, no problem.
No, fantastic presentation. So thank you very much, Iain and Matt. No, we're probably just gone past 2 o'clock, but I mean, some really interesting presentation, and I think the real life examples of bring it together, especially on sites people may be working on it as we speak. I don't know if people who are attending can unmute themselves, and maybe we can just give a round of applause to Matt and Ian, and thank them for their time today and the presentation.
Thanks both.